Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the fourth lecture for chapter 6, counting, in the course CS131 Discrete Structures offered by FCSE at JK Institute. I'll be talking about binomial coefficients and identities in this particular section. What we've discussed so far, just a quick brief overview of what we've discussed in counting is we have discussed some of the rules of counting, namely the sum rule, the product rule, the subtraction rule, and the difference and the division rule. We discussed the importance of the tree data structure, and not data structure, but the tree diagram in in counting and in enumerating. We then discussed in section 6.2, we discussed some properties, again, basically the pigeonhole principle and the generalized pigeonhole principle. In section 6.3, we then talked about some other things, including combinations and permutations. So in this lecture, I'm just going to use those combinations and the formulas, etc., to talk about the binomial coefficients and binomial identities. These are very important things in mathematics, and these are some of the things that are also very significant for computer science as well. And we'll see that these limit our calculations a lot. They help us in calculating things in a very important manner, particularly for binomial equations and binomial identities, and we'll see them in this particular section. I'll be using the board a lot, so I'll be continuously shifting between, live lecture and between on the board. So you need to stay on with me. Okay, so when you talk about binomial theorem, and this I hope you've heard already, binomial theorem is basically a plus b raised to power n, or x plus y raised to power n, or whatever. In elementary algebra, the binomial theorem or binomial expansion describes the algebraic expansion of powers of a binomial. So you've got two binomial and you want to basically, there's a sum between them and they're raised to a certain power and they have to expand it. That expansion is what is called, what is done through binomial theorem or binomial expansion. According to this particular theorem, it is possible to expand the polynomial x plus y to the power n into a sum involving terms of the form axb, yc, where the exponents b and c are non-negative integers with b plus c is equal to n, and the coefficient of each term, a, is a specific positive integer depending on n and b. What this tells us simply, in simple words, is you have to expand the polynomial x plus y to the power n, and that can be done into some form which we call here, which contains x raised to power something, y raised to power something, and then it has a coefficient a. So let's say that x raised to power b, y raised to power c, and with the coefficient a. There are two properties of this. First of all, the coefficients, the sum of the coefficients b and c for this particular expansion ax, b, y, c, b plus c will always give us n. So for example, and we'll see that in a minute, different examples of this. The sum will always be same as n, and also the a will also be depending on the values of b and c and n, in other words. So we'll talk about it in a minute, how the a coefficient is dependent on this, but the other things are, I think, pretty clear here. So for example, if you take n is equal to 4, x plus y to the power 4 is, if you just expand it normally, it is x plus y multiplied by x plus y multiplied by x plus y multiplied by x plus y. And if you expand them using your own formula or whatever, it is x raised to power 4 plus 4x cubed y plus 6x square y square plus 4x y cubed plus y to the power 4. And if you look at this expansion, look at these points. So x to the power 4 is same as the original power, right? And then I can consider y as 0, right? Y raised to power 0 over here, and a as 1 here. So it's 1. If I talk about a, it's 1, 4, 6, 4, 1. If I talk of the power b, that is 4, 3, 2, 1, and 0. If I talk of power c, it is basically 0, 1, 2, 3, and 4. So what do you notice from this? There are some certain things, some certain subtle things that one can notice here. One of them is that the sum of this 4 plus 0, 3 plus 1, 2 plus 2, 1 plus 3, 0 plus 4 is always equal to this particular number. So n is equal to b plus c. That was the first property. The second property one may note is that the value of x is continuously, the power of x is continuously decreasing. So for example, here it's 4, 3, 2, 1, 0. The value of the power of y is continuously increasing, 0, 1, 2, 3, 4. And then of course we'll talk about how the coefficient is being computed. And the coefficient in this case is always computed by the formula C and B. It just uses the combination formula. So in this case, n is 4. And in this case, B is basically 4. Or B can basically be 0 as well. You already know through the through a theorem in the previous section that C and B is equal to C and n minus B. And because that is true, hence, and we know that, in this case, it's always the sum remains n. So it is, if x raised to power n itself, then of course Cn4 or Cn0, C44 or C40 gives you the same value. C43 or C41 gives you the same value 4. C42 or C42 gives you the value 6. C41 or C43 gives you the value 4 again. And that is something that you can actually verify as well, that the coefficients can be determined directly. Of all these coefficients, they can be determined by using the formula combination of NB. Remember, the combination can be represented without, with just as NB, as I'll show you in the next slide, without C as well. So that's another way of representing it, and we'll talk about it later. These coefficients for varying n and b can be arranged to form something which we call Pascal's triangle. So what is a Pascal triangle? We'll discuss that in the next slide a little bit, and maybe in more detail in the later part of this particular lecture. But for introduction, I think it's necessary to know that you can arrange these coefficients into a Pascal triangle. And of course, we've already studied these combinations and combinatorics in the previous section, where C and B gives the number of different combinations of B elements that can be chosen from an n element set. This is R combination. This is B combination in this case. So that's the whole thing. So what is a Pascal's triangle? It's discussed in more detail in the next slide, but here I just need to point out two or three particular characteristics of Pascal's triangle. A Pascal's triangle is something where you start from 0, 0. This is a typical representation of a combination. So this is like saying that C0, 0, C10, C11, C20, C21, C22, C30, C31. So if you see something like this without brackets, without a C or something mentioned, this is only combination. This is not permutation. For permutation, you need to use P and R. There's another way of writing combination and permutation, but I'll not go into that detail for now. For now, you just need to know that these brackets represent combinations. So this is basically saying selecting 0 elements from a set of 0 elements where the order doesn't matter. So this is C00. This is always equal to 1. Similarly, C10, selecting 0 elements from 1 element in total, or selecting 1 element from a total set of 1 elements is C11. So both of them are also 1. Selecting 0 elements from 2 elements is 1. Selecting 2 elements from 2 elements is also 1. And you can actually fit in the formula to verify these numbers. Cnn is 1, Cn0 is 1. So these are nn, these are n0, this is nn or n0, and this is basically n0 and nn and so on. So one notices that you have got ones at all the outer boundaries of this particular triangle. So if you put them all, enumerate them like this, such that you are incrementing it by one, n by 1 in each row, and then and in each column you're incrementing n by 1. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, and you are adding in all the other numbers in between in the middle of the previous two. As you can see here, it's always in the middle of the previous two. You're basically expanding it by 1 element in each row, and in each row you're basically incrementing the n by 1, and basically the number of combinations or the one combinatorial value is being increased in each row. There is another very subtle property. One property is that all the boundaries, all the edges here, the outer edges of this particular triangle or a triangle are all one, because they're either Cn0 or they're Cnn. That means they're all equal to 1. The other thing here is that each value, if you take each of these values, if you evaluate them, for example, in this particular case, it shows that 75, C75 calculated. This is 7 factorial divided by 5 factorial into 2 factorial. So this comes out to be basically 21. This value, instead of computing it directly, there's a shortcut with which we can compute it. And that is by simply taking the sum of the previous two values that are right above this number. So for 7.5, we can basically say that this is going to be a sum of 7.5 is sum of 6.4 plus 6.5. C6.4 plus C6.5 gives us C7.5. And this is exactly what we note in the triangle as well. 21 is sum of 15 plus 6, and so on. You can actually take any pair here, any combination here, and that is going to be sum of the previous two pairs, the ones that are right above. 35 is sum of 20 plus 15. 35 is sum of 15 plus 20. 21 is sum of 6 plus 15. 7 is sum of 1 and 6. And of course, the borderlines are always 1, so you don't need to compute them. Similarly, 28 is sum of 21 and 7, and so on. So this is basically 8.6 is equal to 7.5 plus 7.6. Take 8.3. This is going to sum of 7.2 and 7.3. So this is one property that we can observe here. More in detail in the coming slides. So let's formally discuss what a binomial theorem is and how we can expand an equation using a binomial theorem. So for that, let x and y be variables, and let n be a non-negative integer. So n is a non-negative integer and x and y are two variables. Then x plus y raised to power n is nothing but sum of j is equal to 0 until n. C and j is combination of n. We have to select j elements from n elements where the order does not matter. It's a combination. So c and j multiplied by x n minus j, x raised to power n minus j. So x has the power n minus j. The first term is going to be xn. The second term is going to be xn minus 1. The third term, because j will be 0 first, then 1, then 2, and so on. So xn first, n minus 1, n minus 2, and so on. X has those powers. Then this is multiplied by y to the power j. Y to the power j is basically y to the power 0 at the start, then y1, y2, y3, y4, and so on until you reach yn. That is the point where x has a power 0, cnn, x0, yn. And this, cnn is 1. So this is 1, this is also 1, and in between you have got some values depending on n and j. So if you expand this expansion, this becomes cn0 xn plus cn1 xn minus 1 y plus so on until cn n minus 1 xy n minus 1 plus c, choose n from n elements, y to the power n. So the binomial theorem simply states that when x and y are variables and n is a non-negative integer, then x plus y to the power n is equal to sum of j is equal to 0 till n. Choose j elements from n elements. That's the coefficient of this particular term. And the term is explained by xn minus j, yj. So this is n0, x to the power n, y to the power 0, plus n1, x to the power n minus 1, y to the power 1, plus so on until you basically reach n minus 1, x raised to power 1, y raised to power n minus 1, plus nn, x to the power 0, and y to the power n. So you need to remember this formula. You can maybe pause here. You can kind of learn this. This will be given to you, I hope, separately. But this is something that you can easily learn by heart. This is a very simple formula. And this is what is called binomial expansion. Let's take a small example. I'll actually try to solve it on the board so that you are clear about it. What is the expansion of x plus y to the power 4? Solve using binomial theorem. So one way of doing this that you can try on your own would be to multiply x plus y 4 times and come up with an answer. If you do that, I'll give you 0 marks. The reason we have to solve it using binomial theorem. So what does binomial theorem state? Let's come to the board and let us discuss it in more detail on the board. What does binomial theorem actually state? What does it want us to do? And that is something which is very interesting and important. So I'll bring this closer a bit. I'll stop sharing for now. And yeah, this brings me to the board. We can kind of discuss the board. So remember the question. The question simply states that we have to expand. I'm getting it correctly. We are supposed to expand x plus y to the power 4, right? What is x plus y to the power 4? The simplest way that you might try is x plus y multiplied by x plus y multiplied by x plus y multiplied by x plus y that we did earlier. But the question specifically wants us to do it using binomial theorem. So with binomial theorem, I have to put in the formula j is equal to 0 until n, right? This is a summation. Then you've got a combination of n j. Then you've got x to the power n minus j, y to the power j. So this is the overall formula. What is j here? What is n here? N here we can identify as 4. So just plugging in the value of n here, you basically get summation from j is equal to 0, 4j x 4 minus j y j. Okay, and by this simple expansion, I'm going to get 4 0 x 4 y to the power 0 plus 4 1 x to the power 4 minus 1 now, which is x to the power 3, or let's write it out, 4 minus 1 y to the power 1 plus 4 2 x to the power 4 minus 2 y to the power 2 plus 4 3 x to the power 4 minus 3 y to the power 3 plus 4 4 x to the power 4 minus 4 y to the power 4, right? So these are terms that are there. And now I can evaluate it. What is 4 0? Combination of 4 0 comes out to be 1. So here the answer is x to the power 4. Y to the power 0 is also 1, so I'm not going to write it out. Plus 4 1 is basically 4. X to the power 3, y to the power 1. I can write it directly, y. Then the next value is, again, 4 2 is basically 6. X to the power 2, y to the power 2. And this comes out to be 6x squared y squared. So that's there. 4 2 combination 4 2 is 6. So I've written that here. In combination, this 4 3 is equal to 4 1 is equal to 4 x x power 1 and y cube. So I don't need to write 1 at all. And then finally, I've got this fourth term, which is 4 4. 4 4 is also 1. So I don't need to compute that. And it's x to the power 0, which is also 1. So 1 into 1 is 1. And then you've got a y4. So this is the answer. And this, you can know, is also exactly the same answer we got from our previous example. So I think I will now move on to the slides again, and we can see the possible solution over there, how it was solved over here. So over here, it's basically, again, it goes through the same formula from the binomial theorem. It follows that exactly this, and that's how I exactly did it on the board step by step. Okay, so what next? Another example. What is the coefficient of x raised to the power 12 y 13 in the expansion of x plus y to the power 25? So this is a slightly different question. Do you need to expand all of this, or can we directly find it for x 12 y 13 for n is equal to 25? The answer to that is clearly that I'll just maybe rub it out and I'll go through it again in a different manner. So this is the formula that we have. X plus y to the power n. When n is equal to 4, then you can fit it in however you want, but this is the thing. So here the question is, for for n is equal to 25, we should be able to find it for, yeah, now it's better. So x is equal to 20, n is equal to 25, we have to find it for the term where it is basically x12 y13. So here it's x12 y13, and this term nj is something we want to find. So this is like saying, what is the value of n and j? If you find that, you just need to find a combination of nj to answer it, and you don't need to compute the whole binomial expansion. How do you do that? Well, the answer would be, I would actually go for it by using some form of what you call. I'll actually make it straight, I think. So now it's better. What should I use here? I think look at J. J is always something that is over here. So I know that the value of J here is 13. The value of N is 25. The value of J is 13. So all I need to do is find the combination of 25 and 13. And this, of course, is equivalent to 25 and 12. So if you find either of it, you're still fine. And this is something that you need to find. How do you find it? I think this is then, you can just put it in the calculator as 25 factorial divided by, for example, 13 factorial multiplied by 25 minus 13, which is 12 factorial. And this is the overall answer to your, this is the coefficient of the term x to the power 12 y to the power 13. So this is the value for this. And this is the coefficient. That is exactly what was inquired in the question. So if you go back to the question now and see what it's asking us the same thing. From binomial theorem, it follows that this coefficient is 2513 or 2512. It's basically the same. As you can see, just the order will change, and the answer is 55,200,000 and 300. So let's talk about next example then, which is example 4. In the next example, it says, what is the coefficient of x12, y13 in the expansion of 2x minus 3y to the power 25? This is a slightly tricky question. And how do you solve it? Maybe pause for a minute, think of it, and then I can try to solve it for you. In the meantime, I'll just go back to the slide here. I'll stop sharing and I'll come to the board. So look at the question again. The question says x12, y13 in the expansion of 2x minus 3y. Yeah, so how do you go about it? I think you can solve it by using the same formula here. But here is a bit of a problem or a trouble that you need to identify. The formula now is not x plus y. It is basically 2x minus 3y raised to power 25, and the coefficient they're asking us for is x12, y13, right? How do you find it? How would I find it? What I note here is that x is basically, it's not x, it's 2x now. So for me, if I just expand this formula, this is going to be summation j is equal to 0 to n. And here is, I think, now 25, as we know. So j is equal to 0 to 25. We've got 25j x. And x here is not x, it's basically 2x. So 2 to the power 2x to the power n minus j, which is 25 minus j, multiplied by minus 3y. It's a negative term. So it's a negative term. So it's minus 3y raised to power j. So it's 25 minus j and 3 minus 3y raised to power j. So this then comes out to be summation 25j is equal to 0, 25j, 2 to the power 25 minus j, multiplied by minus 3 to the power j, multiplied by x to the power 25 minus j, multiplied by y to the power j. So this is it. These three parts, this part, this line, and this line, this is what is my coefficient, and this is what I need to compute. So what is j here? From this, I can know that j is equal to 13, right? Again, so in this case, it is going to be, my coefficient is 25, 13 multiplied by 2 raised to power 25 minus 13 is 12 into minus 3 to the power 13, right? And this is my overall coefficient. Now notice one thing. Does the order matter here? So yes, it does. It did not matter when you had 2513 or 2512, right? So that thing didn't matter. But over here, it does matter. So this is this multiplied by this multiplied by this. This is your overall answer, 2 raised to the power 12 multiplied by minus 3 raised to the power 13, which is going to be a negative number, and this is your overall answer. So let's go back and see how this answer was evaluated in the slides as well. And this is what you notice. When you go back to the slides, you notice that the answer is exactly the same. Its summation, its first exponent is these. Consequently, the coefficient of x12 by 13 is the expansion of obtained when j is equal to 13. So j is equal to 13 is important. If you take j is equal to 12, these values will be different. And that's now how it should be. So hence, it's basically 2513, 2 power 12 minus 3 to the power 13, 2 power 12 minus 3 to the power 13, as is shown here. And this is, you can pick up the value, whatever, compute it and come up with it, or you can just leave it at this point, and this is the right coefficient. Let's take another corollary that we can analyze from this. So let n be a non-negative integer, then summation of from k is equal to 0 to n, combination of nk. So combination of all, sum of combinations of these numbers where they are basically varying from 0 to n is 2 raised to the power n. How did we get there? That's a very interesting point. How do we get this particular formula? Let me prove it to you in over here. I think I can go back to the slides. I can stop sharing, go back to the video, and talk about how to get the corollary out. So the corollary is something like this. It basically says that summation of all numbers j is equal to 0 to n and j is equal to 2 to the power n. How did it get 2 to the power n? How can we prove this corollary? The answer is very simple. 2 to the power n, we can represent it as a binomial equation. How can we represent it as a binomial equation? Well, 1 plus 1 to the power n, this is a binomial equation. If this is a binomial equation, we can simply expand it to something like 1 plus 1 to the power n is can be expanded further, and this comes out to be what is 1 plus 1 to the power n? If I use this particular formula, this comes out to be summation n j is equal to 0 n j 1 to the power n minus j multiplied by 1 to the power j, right? And because this is 1, x is 1, y is 1, so I've taken 1 here, and this 1 raised to the power anything is 1, and 1 raised to the power anything is 1. So this is equal to summation n j is equal to 0 and j and 1 and multiplied by 1. And this we know is equal to summation n j is equal to 0 and j, which is your left hand side. That's it. So take the right hand side. This is your right hand side. This is equal to 2 raised to the power n. I can always expand that. Right hand side is equal to this. Then using the binomial theorem, we can actually expand it. So this is a very simple way to prove a really complex equation. How do you prove these two together? One way is to show it that it exists for all values of n, which is very hard to do. The other way is to prove it in a formula in a generic way. And this is the way you should go by with it as well. So going back to the screen, and there we can discuss how they did it. Using the binomial theorem with x equal to 1 and y is equal to 1, we see that 2 raised to the power n, which is right hand side, is equal to 1 plus 1 to the power n, which is equal to this thing, and so on. We can continue on with that. This is how they prove it, and this is absolutely right as well. So I'll now rub it out and see if something else is required or given as a keeping the binomial equation in mind. So, okay, another corollary. This one says that summation nk is equal to 0 minus 1 to the power k and combination of nk is equal to 0. How do you prove it? My idea here would be to take 0, expand it as a binomial expansion, and then, you know, come with, let's see if the terms is equal. So in this case, I want to prove summation n k is equal to 0 minus 1 to the power k and k is equal to 0. So this is something that we need to prove, right? And if I come back to the board now, this is what we need to prove. Now taking my right hand side is equal to 0, I can run it as 1 minus 1 to the power n. Can we do that? 1 minus 1 to the power n. This comes out to be from this particular binomial expansion. We can come up this can be written as summation n j is equal to 0 n j 1 raised to power n minus j minus 1 to the power j. Is it correct? Okay, so if this is true, I've just expanded this one into this. X is 1, y is minus 1, and I can represent it like this to avoid confusion whatsoever. And now we know that 1 raised to power anything is 1. So then this comes out to be summation j is equal to 0 to n j and this then is equal to minus 1 to the power j as well, right? So this is the overall thing. By the way, there's a small mistake here. I think instead of taking j, if I take k, because this is just the syntax, so it does not matter. I should take k. So this is exactly this. This is equal to the left-hand side. Hence, prove that this value is equal to 0. Since both sides are equal, so this is how it should be. Okay, so let's go back and see how we did it in the lecture, and then we can talk about how this was done. Yeah, so you notice the same thing, 0 as 0 to the power n, right? And then 0 to the power n, and then be 1 minus 1 to the power n, and so on, and it goes on. And that's how it proves it again. However, there's one more thing. If we take this from corollary, we can actually imply that this is equal to n0 plus n2 plus n4 plus so on, and this is equal to the, so anything that is even, the sum of all the even terms in the combination is equal to sum of all the odd terms in the combination. And that is true because when you expand this one, you notice this is a summation, right? So minus 1 for all the odd terms is going to be positive, and for all the even terms, it's going to be negative. So if this is a negative term, then this becomes sum of all the negatives. So these are subtracting terms, and there are some terms that are the positive terms that are going to add up together, and sum of all of them would basically be ultimately equal. Hence, if you subtract the odd terms from all the even terms, you'll basically get a 0 at the end. So this is something that is implied from corollary true. I won't go into the proof of it, but something that you can do it on your own. Similarly, let n be a non-negative integer, then this is something that we have to prove in the corollary 3. How do you do that? The answer is again simple. Take this right-hand side. This becomes 2 plus 1 raised to power n, and then you just expand that equation. 1 raised to power anything will be gone, and you'll only remain with the term that contains 2 to the power k and k, and this is going to be your final result as well. This is exactly what is shown here. It just converts it into 1 plus 2 to the power n, and 1 is gone, 2 remains. But here the order does matter. Keep that in mind. It matters because otherwise you'll basically, if you take it as 2 plus 1 and not 1 plus 2, then it's going to be 2 raised to power n minus k. And you don't want n 2 raised to power n minus k, you want 2 raised to power k. So here the only trick or thing that you need to keep in mind is that 1 should be your x, 2 should be your y. So if you talk about the Pascal's identity, together with the initial condition Cn0, Cnn, which is equal to 1 for all integers n, we can use that to recursively define binomial coefficients. Instead of calculating each value itself, we can just use the previous two calculated values and define the binomial coefficients. Recursion is something that we'll discuss or you'll see in the CS103 course, in the computing course. Anyway, for now, we don't need to worry about what recursive definition really is. Here, what we mean to say is that if you're able to define the two previous values, you can always compute the next value by just using them instead of computing the whole values again. This saves us a lot of multiplications and a lot of other expensive operations. And this actually helps us in computing a lot of things in a really smoother way. And this is something that I discussed before as well. So for example, 7.5, if you want to compute it, it can be computed by computing the previous two values, 6.4 and 6.5. If you know them as 15.6, you don't need to compute 7.5, but directly basically just add 15 plus 6 to get 21. Okay, so what is Vandermonde's identity? Vandermonde's identity simply states that let m, n, and r be three non-negative integers such that r does not exceed either m or n. R is always less than both m and n. So then combination of m plus n, and if you want to choose r elements from the sum of m and n, then this is equal to summation k is equal to 0 to r m combination of m r minus k and combination of n k, right? So there's just a formula that you need to, maybe that will be given or that you need to remember a bit, and we'll see the different applications soon. So the corollary that follows is that if n is a non-negative integer, then 2nn, if you want to choose n elements from 2n, then this is equal to summation from k is equal to 0 to n, nk whole square. This is because from the Vandermonde's identity, this is equal to nn multiplied by nn. And hence this is basically nk whole square that you're going to get. So for example, if you want to choose n, then this comes out to be, if you go back a bit, this is n plus n, we can represent 2n as n plus n, and then n plus n simply comes out to be n plus n and n, summation k is equal to 0 to n, n, 2n minus n, and n, nk. So this is exactly equal to be like this. And the theorem that we can talk about is let n and r be non-negative integers with r is less than or equal to n. Then combination of n plus 1, choose r plus 1, is equal to summation j is equal to r to n and combination of jr. How do you get this? Well, the idea is again simple. N plus 1 can be divided further into n and you add 1 to it. And that's how this is done. So before going on to the next section, maybe I'll try to basically prove it. So how do I prove it? The answer for that is, if I go back to this particular Vandermonde's identity, and we'll just write it out on the board for now, and then we can discuss it in a minute. Before I move on to the next section, I really want to prove this particular theorem. Vandermonde's identity simply states that m plus n r is equal to summation r k is equal to 0, m r minus k n k. This is the Vandermonde's identity. And if you have to prove this, this is really simple. And here we want to prove 2n is equal to summation n k equals to 0 n k square. And if I move to the screen here again, this is what we want to prove. So I can simply take this one, take the left hand side. Right? And the left hand side we can simply say is n plus n divided by n. And then from Vandermonde's theorem, we can simply say that now this is equal to summation. R here is n, So summation till n k is equal to 0, right? M here is n, so n and r minus k. So r is n minus k, right? Multiplied by n, this is the other n, and this is basically k itself, so k is fine. So now, this is where you need to apply some knowledge of combinations. You know that C and K is equal to C and K equal to C and n minus K. You know this formula, right? So from this it follows that this is equal to this as well. So this is equal to summation n k equal to 0 n k into n k, which is summation n k is equal to 0 n k whole square, and hence this is equal to the right hand side, and we are done with this proof. So this is one formula way to prove. Let's go to the other one, and yeah, so how do we actually prove this particular one? Again, I think we can use a similar way. I'll just rub it out and we can then discuss things. So to prove that, let n and r be non-negative integers with r is less than or equal to n, then n plus 1 r plus 1. This it says is equal to summation n j is equal to r jr. How do you prove this one? Okay, so how do you prove this one? Well, the way forward would be that I think I need to, this can be represented clearly as basically in this form. So here it's basically r and m plus n. Here it's n plus 1 and r plus 1. So we need to convert this to this particular form, m plus n and r. And if we can do that, then we can kind of just apply this one. And by opening this, we'll get to this particular point. But there's one small issue here. That issue is the sum here is not starting from 0, it starts from r itself. So this means that we need to divide it into two groups. One of them is, if I have to write it out as n plus 1 divided by n minus r plus 1. So this is one group, right? And or let's say, yeah. And from this, these are the parts or the portions that are greater than this, right? So this is what I'm just saying, that this, if I take n plus 1 divided by r plus 1 combination, this is equal to combination of n plus 1 until this is the one part. The other part here is that I need to subtract the combination of the remaining things, which is, let's say, n. So if I do that, or actually I've written it in the inverse way, I think. So this is going to be n plus 1 till n minus n plus 1 to n minus r minus 1. So this is equal to this, because in combinations, you need to know that these ones are the upper ones, these ones are the lower ones, and you can basically solve this one further. And ultimately, I think you get to this particular point. So that's something that you need to think about in your solution. And this is something that I leave up to you to solve it. You need to apply this to this through this way to get to the solution. So quickly going back to the lectures, I think this is the last thing, and then we need to wrap up the lecture quickly. So in this lecture, you studied some of the binomial theorem, by some of the binomial expansion, and you studied the binomial identities, the Pascal triangle a little bit. And with that, I think, and you also saw some of the proofs for some very trivial things. In the next lecture, we'll be talking about generalized combinations and permutations, which is again a build up on the topic of combination and permutations. They probably don't have much to do with binomial expansion or binomial theorems, but more about when there's repetition involved and when there's no repetition involved, and a generalized formula for combination and permutation. In this lecture, we basically learned something more about the binomial expansion and the different characteristics of binomial expansion. So I hope you learned something. Try this last example on your own, and I think you should be able to prove it. Again, it's not a very trivial thing, but you need to think on these lines before you're able to prove it. See you in the next lecture, and I hope all the best for all of you. Take care. Allah Hafiz.